Today our new topic is on coastal littoral processes. Earlier we looked at the effect of waves on the coastal littoral transport. Right now we are going to look at the effect of nearshore current. Nearshore current are predominantly generated by wind and wave, and their effect is superimposed on the wave-induced oscillatory motion that we discussed earlier. Nearshore current contributes to both onshore-offshore transport as well as longshore transport. Specifically for longshore transport, they are affected by the alongshore coastal current, which may be generated due to sustained wind blowing along the coast, or they are generated by oblique waves breaking near the shoreline. In the figure below here, we see how oblique waves arrive at the shoreline. They are almost parallel to the shoreline, but not exactly. This incidence wave that arrive at an angle will cause wave-induced longshore current in the direction parallel to the shoreline. Now the incidence wave will carry sediment and wash them up the shore, but then the backwash will move back down in the direction perpendicular to the shore following the beach profile under gravity action. As a result of that, there is a net drift in the direction of the longshore current, whereby sediment which is carried onto the beach is washed down on the down coast direction, and this process keeps repeating itself, causing a net sediment movement in the longshore current direction. Offshore, of course, the longshore current profile varies. It is the weakest near the swath zone. It reaches a maximum further out in the nearshore region and diminishes further away, so that this region where the longshore current is operating will observe the net beach drift. Later, when we discuss about the coastal structure, we will mention that in order to intercept beach drift or longshore current, then any structures that is built must be able to intercept the entire longshore current profile, which means beyond this point. Here in this animated figure, we see how the longshore transport or beach drift takes place. So generally, fine sediments will be carried in large volume over longer distance under the action of the longshore current. So as we move further and further away from a sediment source, then the finer material typically will be deposited further away from its origin. Reversing current may be attributed to the propagation of tide along the coast and coupled with the effect of coral reef acceleration. Reversing current can also occur at inlet of harbor or estuaries, and it is characterized by the flood and the ebb motion of the tide, and so it is responsible for the onshore and offshore littoral transport. Another type of current which is oriented in the onshore-offshore direction is called the reed current. A rip current can happen in a relatively long, straight and uninterrupted shoreline, whereby the continuous accumulation of water in the surf zone cause the water level to rise relatively, and as a result of that, a seaward flowing current will develop to relieve that inequilibrium, and that seaward flowing current is what we call the rip current. Usually the rip current will form and break through the incoming wave at a location whereby the wave height is the lowest, and as the rip current flow outwards to the sea, usually it will scour, it means erode a trough, and that's why rip current actually is relatively dangerous in the coastal region. It can trap or wash swimmers out into the sea. Rip current can also happen if the longshore current is intercepted by a structure built perpendicular to the shoreline. We mentioned earlier that a structure like this can be effective in addressing the longshore transport if it is long enough into the sea. Right here, we look at the effect of this type of structure to the longshore current, whereby since the longshore current has nowhere else to go, so it will have to deflect and move towards the seaside, and that is also a rip current. But longshore current typically will not be just stopped by that. It will still be formed on the down coast side of the same structure, because the longshore current is formed from the incoming wave. So essentially, when we build a structure like this, we can stop the longshore current in this local area only. We can stop the littoral transport up to this point only, but if the incoming wave energy continue to produce a longshore current, then we are still going to have longshore transport on the down coast side of the structure. This is how rip current looks like from aerial photograph. We can see that this white foam represents the incidence wave, and whereas we can see the relief in between the wave, whereby it suggests that there is a seaward flowing current. Because rip currents are dangerous to the beachgoers, so shoreline around the world where it has been observed typically will put up a rip current warning sign. Another onshore-offshore current is what we call undertow. Again, it is related to how the wave energy that builds up in the beach area will find a way to relieve itself to maintain the equilibrium of the water surface. So one of the way for the energy to escape back to the sea is through undertow. So undertow forms usually when rip current is not possible, when the wave height is large. So undertow is also equally dangerous to swimmers, whereby it can sweep people out to the sea.